here, and it's mostly introducing a new way to have mobility on the surface of any planetary body, but focusing on the moon in this case, and specifically focusing on a CubeSat class version of this idea. Let's see where the arrows are here. So where this started was back in the 60s. The guy on the right, Harold Rosen, was having this small satellite idea to be the first geosynchronous satellite for communications. And this is on the top of the Eiffel Tower during the Paris Air Show. And at the time, he was told this is the highest this satellite would ever get, the observation tower of the Eiffel Tower, so observation deck. So 2 years later, one of these was launched. It's called CineCom. It was the first commercial geosynchronous satellite, and actually the first geosynchronous satellite. And since then, in the early 60s, Rosen led the technical team at Hughes Space and Communications, and over the decades built up an empire of spinning communication satellites. Back about this time is when Hughes was big acting off for JPL, and Rosen convinced his management to let him propose a different way to land back to JPL. And of course, that was not accepted by JPL because JPL wanted their design. So he kind of buried that idea, and instead, over the decades, built up this multi-billion-dollar empire supplying communication satellites to the world. Rosen's favorite saying during most of these decades was, if it spins, it wins. He and his team developed most of the fundamental technologies for spinning satellites. And when I worked there in the early 80s, they were supplying about 2/3 to 3/4 of all the communication satellites in geosynchronous orbit, really dominating the industry. So this is a snapshot of their family portrait of all the satellites they built up through the mid-80s. And through the duration of the spinning satellite era, which ended about early 2000s, they launched over 200 of these things. And the takeaway of this picture is that the whole design is very scalable. You can enlarge it for extra power, you can enlarge it for extra propulsion, the delta V, you can do more communications. And the common theme through most of these is they're dual spin satellites, which means there's two sections separated by a bearing. There's a V-spun section, which typically has a common payload and all the antennas, which point to the Earth. And then the spinning drum is the power and propulsion and basic energy control, and that provides gyroscopic stability. That's the fundamental innovation that Rosen and his team came up with. At least 5 satellites have used this technique, this architecture, for solar system exploration. They're just shown here. But you know about Galileo, the Pioneer Venus Orbiter, Giotto's on the left, went by the comet Halley, and then the 2 Japanese Halley flyby spacecraft. These are the only ones I know of. There might be 1 or 2 more, but there aren't that many. But at least it's been used for solar system exploration. So fast forward several decades, as I mentioned, Rosen had buried this idea in his brain, never got to use it. But when the Lunar was announced in 2007, he came out of retirement at age 82 to build a spinning lander. And what he had in mind was very simple. Based totally on this dual spin spacecraft idea, he assembled a team of ex-Hughes people, shown here in his living room in Santa Monica. And we met for almost every weekend for about 6 months developing the concept of Lunar product. And this was called the Southern California Selene Group. Just in this room, that bunch of people there worked on 500 missions at Hughes. Lots and lots of experience. The lander design that was generated, which was the official entry into the Google and Rex Prize, shown on the left, just for size comparison. And again, it's a spinning lander. It's completely novel, and so novel now it's patented. And I was deputy project manager for this effort. And when Rosen folded his team, and that's the lunchtime talk I can get into with you later, if you want to know why. But, he folded the team and bowed out of the competition, but he signed a patent over to my company, Ecliptic Enterprises. And this is generally what a spinning lander looks like. It's a dual spin spacecraft, only it has legs on the V-spun side. That's the basic idea. All the rest of it is very similar to a typical dual spin spacecraft. This one just happens to be about the same size as CineCom, the one I showed in the earlier photo. And in fact, the antenna is exactly the same antenna design as CineCom used in the 60s. And this was the entry to the Lunar X Prize. It has some interesting features. Let's go through these real quick. But very, very small, less than 50 kilograms dry mass, had huge LV capability because it's mostly propellant tanks under there. And was sized for a Falcon 1D launch. I when SpaceX was still selling those. The bicrop system had a standard Star 30 Ember stage to take it to the moon, and the rest of it was taken over by the spacecraft. And the neat thing about these spin landers is they will not tip over because they're gyroscopically stabilized at landing. They have somewhat flexible legs, so they can absorb some of the landing shock and just kind of skitter to a stop. And then once you land, they're fairly benign because they can slowly barbecue, and at least the spun side does. Standard feature of spinners, and then it's also an excellent hopper. Once you land, you can hop to other places. So to win the X Prize, Lunar X Prize, we had to hop about 500 meters. This one had 5 kilometers of hopping capability. And the neat thing is some fairly mature cost estimates were done for this particular design, including the rocket and the upper stage and mission operations. And the whole thing was coming in around $20 to $30 million. So how does that relate to today's talk? No matter what size it is, these spinning landers have the following attributes here. Basic idea is very benign thermal environment because they're spinning. Very robust attitude control. The attitude control system can completely freeze and nothing really happens because you're a gyroscope. You just sit there until you get back online. One thing you need to make a dual spin spacecraft a lander is you need a landing radar, and for a spinner you only need one radar. You don't need 3 or 4 like some landers for 3-axis landers. And then, as I mentioned, it has excellent hopping capability and a very robust landing system. It just will not tip over. And it has other capabilities, sort of qualitatively. Compared to 3-axis satellites, typically the propulsion system is about half as complex, and typically the attitude control system and the flight software is about 1/3 the complexity of a 3-axis. So those are all sort of heuristics you can keep in mind. I won't go through this in detail, but the bottom line was this came about in Harold Rosen's mind in the early 60s. It wasn't really applied until the Google Lunar X Prize came around. And over the last couple of years, I've been presenting this at various conferences related to either small sats or low-cost interplanetary mission concepts. And here I am today presenting it for the first time on CubeSats. For larger landers or different places, these are some of the charts I've been showing at the other conferences. And I think I showed these, Pam, at the one you got intrigued with. But basic idea is it's very scalable. These are not fancy designs, they're just notional. But if you want to go in through an atmosphere like for Mars or Venus, you need to make the whole spinning side more like an aeroshell shape so you can stick it in an aeroshell. So it's more like a gumdrop. If you're on an asteroid or another body that has low gravity, you probably don't have landing legs, but you got spikes or something. Now, I'll go through quickly just the notional design. How does this apply to a CubeSat class lander? I just made some basic assumptions about the kind of mission you might want to do, and then went from there. Let's say you want to go to the polar region of the moon, north or south. You're going to have sunlight coming mostly from the side, and you want to somehow explore those persistently shadowed polar craters. I'm assuming you're going to land a larger lander on the surface close to where you want to explore, and it's going to have several of these spinning landers on board, CubeSat class spinning landers. And you're going to use those for mobility to transverse over to some other place and either land some science or do some science while you're going over there. And then you can have remote sensing or in situ science, depending on whether you're in flight or on the surface. And I made some simplifying assumptions. I figured a 1U CubeSat isn't going to do it because you need a spun and despun interface. So it's minimum probably a 2U. I made it a little longer, and you'll see why shortly. I assumed that all the communications would be wireless back to the mothership and not back to Earth. It's all battery powered. Propulsion system is going to be a challenge, but I just assumed it's going to be there someday. It may not be there right now today, but you can always have propulsion somehow or another. It's got to be fairly high impulse propulsion, not ion propulsion, because you have to hover basically. And various science instruments and multiple cameras. So let's just notionally go through this. Here's a fictitious lander big lander that has plenty of space for more of these little CubeSats. So here's roughly a 3.5 view spinning lander all stowed up. And there are little launchers that launch vertically out of this lander, and you can pop them off one at a time. Each one would have a separate mission to do. Little close-up stowed on the upper left here. You have a mast that's got a couple little webcams on it. It's the communications antenna back of the lander. It's stowed farther down into the CubeSat while you're launching it so the thing doesn't twang. And then later it pops out. You have a descent section, which is the upper cube. You have at least two, probably a little more than two sun sections below, which have the avionics, propulsion, batteries, and probably the payload. And then these legs actually derive from the rails that are along this stack of CubeSats as you go out of this launcher. So deployed, it looks like on the right. Now the key interface here, which I didn't really have until recently, just notionally I knew you had to have one, but it turns out some MIT students did a really excellent paper at the Small Satellite Conference this summer in August and presented a very nicely done dual spin satellite interface for CubeSat class. 5 minutes, I see. And this is basically a commercially available unit that's been modified somewhat to fit their particular interface, but most of the busy stuff is really quite available. If you don't know how a dual spin spacecraft is controlled in both maneuvering for Delta V as well as translating, it's on this chart. I won't go into it, but it's, take my word for it, it's been proven hundreds of times and it works very, very well, and it's really simple. So let's talk about a typical mission where you're going to explore a dark crater. What do you do with one of these? You pop it out of the, you probably command it from the Earth, you pop it out of this lander, it goes up, and very quickly it spins itself up, deploys the legs, and basically turns the comm and the radar on. So before it starts falling down and coming back down to this lander that just launched it, it's up and spinning and in a dual spin mode with everything working. That's got to take just a few seconds. Then using standard dual spin maneuvering capability, the thing has probably a pre-planned program that's been loaded in on where it should go, and it zooms across the width of this crater. I tried to show it going off into the distance, taking images perhaps with some simple cameras that are looking down from the sun side, and then executes a landing on the other side of the crater. And maybe at the landing site it does some in situ science, and then on command, after you're done with that little phase, it does a hopping maneuver, maybe goes right over the top of the crater and then jumps down in the middle of the crater. Maybe all it's doing for in situ science there is setting off a really bright LED and taking a picture of the dark floor of the crater. And then presumably, maybe you don't want to leave it in the crater, maybe you want to dispose of it some other way. Maybe it does a last data blast as it flies over the lander before it retires. But the whole thing would be on batteries. The whole thing would probably last no more than, you know, tens of minutes or maybe an hour, depending on battery life and Delta V and all that. Now there's some issues with this thing as I showed it. One is the spinner needs to normally be about like a tuna can in shape, not a soup can. It'd be a lot more stable as a tuna can. My hunch is this lander, as I showed it, is a little bit short on Delta V, I guess. So I might want to add some propellant tanks. And also I might want to spin the thing up before it comes out of the lander craft so that you don't have to do that with the spacecraft itself. And so maybe for version 2 of this, I show more like a spin table on the lander craft that spins this whole thing up. It has extra tanks on the spun side, which gives it more stability and probably makes it more stable inherently and gives it a whole lot more Delta V. So otherwise, it's a very similar idea. But you can see where the core is a CubeSat and it has a lot of potential. So these are the 3 things that I think are the most critical to solve with that first version. And I think something like this would do it. So where we are now is I'm here mostly to sit in all 3 days and just discuss mission ideas where this might apply, because certainly it applies to lots of different things. You could put magnetometers out there, maybe laser reflectors around the lander site itself, do in situ science. There's some subsystem requirements that I need to understand a little better on guidance, navigation, and control. You know, how accurate does this thing have to work, especially propulsion, delta V. There's some technologies I think are probably not quite ready for prime time on this, most likely propulsion, and that would be worth discussing if anybody knows the latest on that. And then there's integration issues not only with the lander itself, but how you integrate the lander with this mothership, if there is one, and how you make everything more elegant and simple. So once you have some notional ideas in mind, I think it's great to have some concept art like this and maybe some mission animations just to show what you can do with it. But I'm all ears, so here's my contact info, and I'll be here all 3 days. Okay.
Thank you very much.